For decades, computing has operated under a strict rule of passivity. Software sits idle, it waits. It does absolutely nothing until a human operator types a command and hits enter. The tool is entirely reactive to your explicit initiation. The architecture of an always-on personal agent, like Hermes, discards this reactive model. These systems maintain continuous memory, spawn their own routines, and initiate tasks without waiting for a prompt. Here is an animated diagram showing how Hermes routes continuous data streams. It operates across multiple environments simultaneously, carrying context from a local command line, pushing code into a secure cloud server, and messaging stakeholders in a chat interface, all on its own schedule. This shift transforms the computer into a mixed-initiative collaborative entity, one that decides when to act, when to pause, and when to interject in your workflow. Empowering an intelligence to act in the background of your daily life creates a new category of risk. Integrating these systems into the operating system of daily life requires a control philosophy designed specifically for persistent agents. There is an assumption that delegating tasks to autonomous software automatically reduces human workload. The empirical reality is the supervision paradox. The workload shifts from active execution to relentless supervision. Without strict calibration, an agent attempting to be helpful will bury you in constant pings for micro-approvals. This relentless task switching induces a documented organizational phenomenon known as AI brain fry, a state of extreme cognitive overload and decision fatigue. When a system pushes continuous notifications for minor successes or low-priority queries, human sensory thresholds adapt. Operators develop asynchronous alert fatigue, treating these pings as baseline noise and virtually guaranteeing they will ignore an actual critical security alert. This exhaustion leads directly to approval fatigue attacks. A mentally drained engineer seeking to clear their screen begins reflexively rubber-stamping prompts without actually reviewing the payload, inadvertently authorizing malicious actions. When an agent operates without boundaries, it stops being a productivity tool and becomes a drain on the operator's attention, eventually serving as an automated attack vector against system security. To control an always-on agent, the architecture must enforce a principle called effective sovereignty. The system cannot function as an independent entity competing for your attention. It must act as an asynchronous, deferential extension of your cognitive footprint. This means the agent must operate under a strict interruption budget. It is allocated a finite number of proactive engagements per day, aggressively delaying non-critical prompts to protect your focus. Human tasks are structured hierarchically into subtasks. When you finish writing a function or sending an email, your mental workload temporarily decreases. These boundaries are natural cognitive breakpoints. Hermes is engineered to detect these moments contextually. It infers a breakpoint by monitoring for an extended pause in your keystrokes, the closing of a primary application window, or the successful termination of a long-running compilation script. If an agent interrupts you in the middle of deep knowledge work, it forces you to abandon your current mental model to evaluate its prompt. The cognitive process of reorienting back to your original work carries a high cost known as task resumption lag. Systematically deferring agent communications until a verified cognitive breakpoint is the only reliable method to combine machine proactivity with human focus, avoiding complete desynchronization. Agent autonomy cannot be treated as a simple binary toggle between full control and full manual prompt. It requires a dynamically graduated spectrum, evaluating the mathematical reversibility and urgency of every proposed action. This flowchart maps the agent action and approval routing logic, the exact evaluation pathway an autonomous system must execute before initiating any task. The first operational gate tests whether the action is externally visible. The agent must determine if the task modifies an external API or touches a public platform, or if it is entirely local. If the action does break the containment of the local environment, the system moves to the fully reversible check. It analyzes the specific command to see if the action creates a permanent external state change. If the action is isolated, confined within an ephemeral Git work tree or a Docker container, reversibility is guaranteed. The agent defaults to the execute silently terminus, proceeding without human authorization because any error can be cleanly discarded. For actions requiring complex state changes, the agent must pass the context recent requirement. This measures the freshness of your operational instructions, verifying that the preferences recorded in memory still align with current operational reality. If the memory is stale, the system applies context-aware permission degradation. It automatically downgrades its own operational status, shifting to the queue for approval or interrupt immediately pathways to force a manual recalibration of your intent. Safe autonomy is strictly an engineering function of containing the blast radius. A viable system systematically defaults to human-in-the-loop validation anytime it encounters an irreversible external action. When operators first use an advanced AI, they experience a honeymoon phase known as algorithmic appreciation, readily delegating complex tasks. But this dynamic learned trust is exceptionally fragile. The relationship is highly susceptible to single-error shock. A solitary, unexplainable failure by the agent completely shatters the operator's trust, causing a permanent decline in future reliance. This trust erosion accelerates when agents present hallucinated or incorrect results with absolute linguistic certainty. This presentation of fake confidence disables your ability to accurately gauge the system's actual reliability. To prevent this, interfaces must utilize trust calibration cues. These are specific linguistic and visual triggers embedded in the agent's messages, openly declaring internal uncertainty and system limitations so the operator knows exactly when to verify the output. When the agent hits a boundary, presenting a generic "should I execute this?" prompt inevitably leads to blind rubber stamping. Instead, the agent must use an escalation ladder, a structured message explicitly defining the context, the proposed technical action, and the specific risk level before execution occurs. The linguistic framing of AI outputs is not a matter of aesthetics. It is the primary security layer required to enforce human accountability and prevent dangerous over-reliance on generative algorithms. This animated diagram visualizes the emerging threat of indirect prompt injection. If an always-on agent proactively scrapes external web data to summarize a ticket, it can unwittingly ingest a hidden payload, executing an attacker's commands and functioning as a fully automated attack vector. Because these agents build cross-session user models, they introduce severe privacy vulnerabilities. An agent storing data from an isolated, highly confidential project might inadvertently retrieve and broadcast that sensitive context while assisting you in a multi-user public channel. Operators must deploy strict profile segregation. This means maintaining a starkly restricted read-only profile for social messaging gateway duties, separated entirely from the permissive profile bound to your secure local coding environments. The agent's permanent approvals require meticulous allow listing. Granting wildcard approvals to powerful system commands, rather than restricting them to immutable read-only scripts, guarantees automated infrastructure destruction the moment an agent hallucinates. Because persistent memory intrinsically generates longitudinal vulnerabilities, the security of your system is entirely dependent on the strict operational boundaries you configure on day one. Architectures like Hermes significantly advance the frontier of personal automation, introducing closed learning loops and cross-platform reach. But the human-computer interaction science surrounding trust calibration and contextual permission degradation is still maturing. For technical power users, deploying a persistent agent is highly recommended today, provided it's strictly governed as an asynchronous, bounded operational sidecar rather than an unbound proactive surrogate. Until advanced HCI features like bounded cognitive compressors for managing memory drift are natively built into the core engine, defensive configuration is mandatory. You must enforce aggressive gateway routing to silence baseline noise and confine autonomous coding loops entirely within isolated work trees. The viability of a persistent agent rests on its ability to minimize the cognitive cost of its own supervision.